The Internet connects billions of devices globally, creating a vast network of interconnected systems. This network facilitates communication, commerce, and collaboration on a massive scale. It's a complex web of hardware and software working together seamlessly. Have you ever wondered how information travels from one computer to another across the world? The journey of data is a fascinating process involving various protocols and technologies. Understanding this process sheds light on the inner workings of the Internet. The answer lies in the network layering model, a conceptual framework that divides communication into distinct layers. This model simplifies network communication by breaking it down into manageable components. Each layer performs a specific function. Indeed, each layer has its own purpose, from sending electrical signals through physical cables to displaying a web page on your screen. These layers work in harmony, ensuring data is transmitted efficiently. Every layer plays a crucial role in the process.
The transport and application layers are where digital communication becomes more human-friendly. They effectively bridge the gap between complex systems and seamless user interaction. These layers ensure our digital interactions are seamless and easily understandable, making technology accessible to everyone, regardless of technical expertise. Specifically, the transport layer ensures data gets to the correct destination reliably and efficiently, thereby optimizing overall network performance. It handles data segmentation, transfer, and reassembly processes, ensuring data integrity and preventing corruption during transmission across networks. Meanwhile, the application layer deals directly with the services we use daily, including web browsing, email, and various file transfer protocols. These services make the Internet accessible and incredibly useful, empowering users to effortlessly connect, communicate, and collaborate seamlessly. Together, the transport and application layers are fundamental to our modern digital experience, enabling reliable and user-friendly interactions in the digital world.
Welcome to our guide on understanding port numbers, a fundamental concept in networking. Imagine your computer as a big building with hundreds of rooms. Each room handles a different kind of service, one for web pages, one for email, one for games, and so on. These rooms are called ports, and they're identified by specific port numbers. For example, port 80 is commonly used for HTTP web traffic, allowing you to browse websites. Email services often use ports like 25 for sending mail and 110 for receiving it. Other crucial ports include 21 for FTP, 53 for DNS, and 443 for secure HTTPS connections. These numbers ensure that data packets reach the correct application or service on your computer. Without them, your computer wouldn't know where to send incoming information, leading to chaos. Understanding ports is key to grasping how networks communicate and how your devices function securely. Thank you for watching, and we hope this explanation helps clarify the role of port numbers in computing. In the vast world of computer networking, port numbers are crucial, acting like specific doorways that allow different types of data to reach their intended applications. These universal identifiers ensure that when you send an email or browse a website, the information goes to the correct service on the receiving end. For instance, when you access a standard website, your browser uses HTTP, which universally communicates through port 80. For secure browsing, like online banking or shopping, HTTPS encrypts your connection and relies on port 443 to ensure your data remains private. When transferring files between computers, the File Transfer Protocol, or FTP, typically utilizes port 21 for its operations. Email services use a couple of key ports. SMTP, for sending mail, uses port 25, while POP3, for receiving mail, uses port 110. Additionally, the Domain Name System, or DNS, which translates website names into IP addresses, operates on port 53. Understanding these common port numbers is fundamental, as it enables network devices to efficiently route data to the precise service it needs to reach.
The first transport protocol we'll explore is UDP, which stands for the User Datagram Protocol. It's fundamentally connectionless, meaning data is sent without establishing a formal connection or checking if it successfully arrives at its destination. Think of it like tossing postcards into the mail. Once sent, you don't receive confirmation of delivery, and some might not reach their intended recipient. This approach makes UDP incredibly fast and lightweight, prioritizing speed over guaranteed delivery. Because of its speed and efficiency, UDP is ideally suited for applications where timely data transmission is more critical than perfect reliability. That's why UDP is extensively used in live streaming, voice calls, and online games, ensuring a smooth, real-time experience.
In real life, apps that rely on real-time performance often use UDP. This protocol is crucial for applications where speed and continuous flow are more important than guaranteed delivery of every single data packet. Think about live streaming or online gaming. A slight delay is acceptable, but constant interruptions are not. For example, when you're on a video call, slight delays are acceptable, but interruptions are not. UDP ensures that your video feed keeps moving, even if a few frames are dropped, preventing a frozen screen. In contrast, a stuttering video, constantly buffering, would make the conversation impossible to follow. UDP allows data to keep flowing smoothly, even if some packets are lost. This is because UDP prioritizes speed over guaranteed delivery, making it ideal for real-time communication. On the other hand, TCP would pause to resend any lost packets, causing noticeable delays. UDP is truly perfect for real-time data applications, ensuring a seamless user experience.
The second core protocol, TCP, the Transmission Control Protocol, is fundamentally designed for reliability. It ensures data delivery is ordered and error-checked, crucial for applications like web browsing and email. Before any data transmission, TCP establishes a connection using a precise three-way handshake. This process begins with a SYN packet from the client, followed by a SYN ACK from the server, and finally an ACK from the client. Once this connection is established, TCP guarantees that every data packet is received in a correct order and without errors. It achieves this through sequence numbers, ensuring data reassembly even if packets arrive out of sequence. TCP also employs checksums for error detection, discarding any corrupted segments. If an acknowledgement isn't received, TCP retransmits the data, ensuring nothing is lost. This robust error handling and ordered delivery make TCP the backbone for reliable internet communication. Whenever you browse the web, check emails, or download files, you're using TCP. It ensures data integrity across networks, making sure everything arrives as expected. It might be slower than UDP, but it guarantees your data arrives safely. This reliability is crucial for important communications. That's why TCP is used for accuracy-critical services like HTTP, HTTPS, FTP, and SMTP. It's the backbone of secure data transfer online. When you open a website, your browser sends an HTTP request to the server. The browser asks the server, "Hey, can I see this web page now?" The server responds with the web page data. HTTP works on port 80 and is stateless, meaning no memory of past requests. Its secure version, HTTPS, uses encryption over port 443 to protect your privacy. HTTPS ensures your information remains confidential and safe.
Today, we'll explore internet protocols, FTP and email, crucial for online info sharing. FTP, or File Transfer Protocol, transfers files between a client and server via TCP/IP. It allows you to manage server files, like updating websites. FTP uses port 21 for commands, port 20 for data. Common uses: uploading, sharing files, backing up data. Standard FTP transmits data in plain text, making it vulnerable. SFTP and FTPS encrypt the connection for secure transfers. Now, email protocols. SMTP, POP3, and IMAP govern email sending, receiving, and storage. SMTP sends emails from your client to the recipient server via port 25. POP3 receives emails, downloading messages to a device using port 110. IMAP receives emails and synchronizes them across devices, keeping them on the server on port 143. IMAP suits multiple devices. POP3, offline storage. Understanding these protocols ensures efficient, secure data exchange.
Internet protocols like Telnet, SSH, and DNS are fundamental to how we connect and communicate online. Telnet, developed in 1969, allowed remote login using text commands over port 23, but it transmitted data as plain text, making it insecure. Modern systems now use SSH, or Secure Shell, introduced in 1995. It encrypts the entire session, ensuring safe and secure remote access, typically over port 22. When you type a web address like www.google.com, your computer needs an IP address, not a name. DNS, the domain name system, acts as the Internet's phonebook, converting these names into numerical IP addresses, operating on port 53. It uses a hierarchical structure from root servers to top-level domains, allowing quick resolution of billions of requests daily. Together, these protocols, along with TCP and UDP at the transport layer, power the Internet from browsing to email. Every click and connection relies on these foundational systems, making our digital world possible.